Hello, today I'm going to talk about quark flavor SU3 symmetry. We will look back at the early days of particle physics and investigate how Murray Gell-Mann brought order to the chaos which the invention of accelerators and cloud chambers wrought. The first elementary particles to be discovered was the electron in 1897 by J.J. Thomson using cathode rays emitted by hot filaments. The next profound discovery, by Rutherford in 1909, was that all matter comprised atoms made up of a concentrated positively charged nucleus, i.e. protons, surrounded by orbiting electrons. Finally, in 1932, Chadwick discovered the neutron, an electrically neutral twin to the proton. However, by the 1950s, countless other particles had been discovered through investigating cosmic rays and synchrotron beams. So many had been discovered, in fact, that William Lamb's Nobel Prize acceptance speech began with the lament that the finder of a new elementary particle used to be rewarded by a Nobel Prize, but such a discovery now ought to be punished by a $10,000 fine. This so-called particle zoo seemed completely indecipherable at the time, and it was unclear how each particle related to one another. In 1961, however, Murray Gell-Mann discovered that he could arrange the observed particles into certain shaped graphs according to two of the particle qualities which could be measured at the time, namely charge and strangeness. For example, there was the baryon octet and decouplet. Each point on these diagrams represented a particle which had been observed. Now keep these shapes in your head, but let us take a detour and investigate the irreducible representations of the SU3 Lie algebra. The SU3 Lie algebra can be represented by 3x3 unitary matrices with zero trace. One basis for this representation is the Gell-Mann matrices shown here. Now from the representation theory of GLN, we know that the diagonal elements form the Cartan subalgebra, so for SU3 we can see that the Cartan elements are going to be lambda 3 and lambda 8. Now let's take a look at the weight space of SU3. We'll first define the two Cartan elements, lambda 3 and lambda 8, as h1 and h2 respectively. As off-diagonal elements are 0, then clearly the eigenvectors are simply the canonical basis elements of C3. The corresponding weights for each of these eigenvectors are shown below, in the h1 and h2 basis. The weights of these three eigenvectors are shown here. Note that they form an equilateral triangle. Let us now examine the irreducible SU3 representations of C3, tensor product C3, tensor product C3. I'll skip over the derivation in the interest of time, but this tensor product is isomorphic to the direct sum of a copy of C, two copies of this 8-dimensional representation on the left, and one copy of this 10-dimensional representation on the right. Technically, these weights are off by a scalar multiple, as they have been defined using generators of 1/2 of the Gell-Mann matrices, as is common in literature. However, the important part is the shape of these weight diagrams. Does it look familiar? Well, we have discovered, as did Gell-Mann himself, that the weight diagrams of the SU3 irreducible representations of C3 tensor power 3 resemble the organizational structure of the particles experimentally discovered. How could this be? Well, let's suppose that each particle in our octet and decouplet is comprised of three smaller subparticles, and each of these subparticles have a three-dimensional state space, that is, C3. In such a case, the state space of each particle would be given by C3 tensor product C3 tensor product C3. In fact, these subparticles are what are now known to be quarks, and the three-dimensional state space is just the flavor of the quark. In this SU3 flavor model, only the up, down, and strange flavors were known. Therefore, the particles observed were combinations of these three flavors. So it was through the study of this SU3 Lie algebra that Gell-Mann discovered the three smaller components which made up the observed particles. What's more, when Gell-Mann proposed his eightfold way, the particle with a charge of -1 and strangeness of -3 at the very bottom had not yet been observed. Using his model, he predicted this particle's existence and even calculated its mass and lifetime. In 1964, the omega- particle was discovered, just as he had predicted. Some important notes, however, are that there is not a true SU3 symmetry among these three quark flavors. Specifically, as top, down, and strange quarks have different masses and charges, then if the state space of particles is acted on by an SU3 Lie group element, then it is likely that many conservation laws would be violated. In addition, each flavor quark has a corresponding antiparticle, and these antiquarks simply have their weights flipped along the h1 axis. Furthermore, we can also take the tensor product of this antiquark representation with a quark representation to get another particle. These particles, which comprise a quark and antiquark, are known as mesons, and there also exists a meson octet in the eightfold way. Finally, while no quarks have ever been observed on their own, the evidence of their existence is overwhelming. The reason why they have been shy to us so far is due to the phenomenon known as color confinement, whereby the energies great enough to pull quarks apart from within a meson, for example, actually create quark-antiquark pairs in between, never allowing for a lone quark to be observed. Thank you for listening.